In this experiment, you will be looking at the Hofmeister effect on polymer solubility. You will see a visual demonstration of the T delta S influence in the Gibbs equation. The stockroom will provide you with a solution of poly N isopropyl acrylamide, which you will be using to measure the temperature at which there is a phase transition. The acronym for the polymer is PNI-PAM. The polymer will be dissolved in water and is stabilized in water via hydrogen bonding. Up to 3 hydrogen bonds can form per monomer unit. The monomer unit is shown in figure 1. Because of the high amount of hydrogen bonding in the polymer, the process of dissolving the polymer from a solid into solution reduces the entropy overall. Therefore, raising the temperature will cause the polymer to fall out of solution based on the Gibbs equation. More about the Gibbs equation can be seen in the video about the theory behind this experiment. In this experiment, you will also influence the transition temperature by placing the polymer in an ionic environment. Start by measuring the appropriate amount of salt to form 50 milliliters of 0.5 molar stock solution. Then qualitatively transfer the salt into the volumetric flask. A qualitative transfer means to rinse the container several times to ensure complete transfer of all material. You are using volumetric equipment in this experiment to have a high degree of accuracy with your salt concentrations. Once you have formed your stock solution, you will need to make multiple solutions of a lower concentration. Sometimes it is not possible to directly measure out the mass needed for a low concentration. That is when you perform a dilution. Additionally, performing a dilution helps reduce the amount of material that you start off with. When performing a dilution, the number of moles you transfer over remains constant. That is what the equation M1 times V1 equals M2 times V2 represents. M1 is the concentration in units of molarity of your initial solution, in this case, your stock solution. V1 is the volume you will transfer from your stock solution to your dilute solution. M2 is the molarity of your dilute solution. V2 is the volume of your dilute solution. You can use this equation in multiple ways. When making a dilution, you generally are trying to calculate V1, the volume you will transfer. You have a target concentration and you have a specific final volume you will be making. When you have made your dilution, you can use the equation to calculate the actual molarity of the dilute solution that you have made by using the actual volume you transferred. Now let's go over an example of your calculations that you will be performing in this experiment. You have a stock solution of 0.5 molar. Your dilute volume will be made into a 10 milliliter volumetric flask. Therefore, your dilute volume is 10 milliliters. One of the target concentrations that you are making is 0.2 molar. By rearranging the equation, you can say that V1 equals M2 times V2 divided by M1. By substituting the numerical values into the equation, you can find out that V1, the volume that you are transferring over, is 4 milliliters. Once you have made all of your concentrations of salt, you will then measure out equal amounts of the polymer solution and one of your salt solutions or water into a test tube. You will repeat this to make 5 test tubes with different concentrations of salt. Then, label your test tubes. Set up a water bath using a small beaker, hot plate, and temperature probe. Make sure the probe is not resting on the bottom of the beaker by clamping it in place. Place your test tubes into the water bath and ensure that they are not bobbing nor tipping over. Be able to observe all 5 test tubes simultaneously. Then, start to raise the temperature of the water bath slowly and observe all 5 test tubes, occasionally swirling the test tubes. Watch for the phase transition and record the temperature at which each test tube performs the phase transition. The LCST is the transition temperature. So delta LCST is the difference in the transition temperature when no salt is present and the transition temperature at each specific salt concentration. You will be graphing all of the salts and all of the different delta LCSC from the entire class on one graph. Make sure when graphing, the scale is appropriate, axes are labeled, there is a graph title, and if necessary, a legend. In this experiment, you will also be performing a nonlinear fit to your SALT data. A nonlinear fit can be difficult for Excel to perform, and there are other programs such as Mathematica or MATLAB that can do this for you. Both Mathematica and MATLAB are free for UCI students through UCI's Office of Information Technology. The website to download the MATLAB software is listed below. Here we have the default view for MATLAB version R2008B. In the middle, you can see the command window where you will type in the commands that you need and the definitions of the variables that you are using. And this command window tells the software to perform calculations and generate plots. On the right, you have your workspace. This is where you can see what you have defined and their values. You can also edit values such as matrices found here. On the left is your current folder where you see any previously saved workspaces. In this experiment, you do not need to go far in depth with MATLAB, just a cursory start. The instructions in the Post Lab deal primarily with the command window and the workspace. I encourage you to download MATLAB and get mildly familiar with the software, as engineering students tend to need this in future classes as well.